Hello and welcome back. Today we're overclocking and undervolting the AMD Ryzen 7 9700X all the way up to 5860 MHz. For that I use asynchronous eCLK to stretch the precision boost frequency beyond its limit. And also we need to use the very new curve shaper tool. In this video, I break down the Ryzen 9 7900X tuning process into 5 unique overclocking strategies for beginners to advanced overclockers. However, before we jump into the overclocking, let's first have a quick look at the hardware and the benchmarks that we'll be using in this guide. The AMD Ryzen 7 9700X is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line, codenamed Granite Ridge. The Granite Ridge processors were introduced on June 2, 2024 during Computex 2024. The Ryzen 7 9700X succeeds the 8-core Zen 4 Ryzen 7 7700X, which we overclocked in SkatterBencher number 47. It has a base clock of 3.8 GHz and a listed boost frequency of up to 5.5 GHz. Unlike its predecessor, the TDP is capped at 65 watt. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course we have to check the performance at default settings. The default precision boost 2 parameters for the Ryzen 7 9700X are as follows. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. Here is the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4105 MHz with 0.957 volts. The average CPU temperature is 56.7 degrees Celsius. The average CPU package power is 87.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4498 MHz with 1.022 volts. The average CPU temperature is 56.7 degrees Celsius. The average CPU package power is 87.8 watts. Of course, we can increase the power consumption limit by utilizing precision boost overdrive, and that's exactly what we'll do in our first overclocking strategy. But before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply leverage the AMD Precision Boost Overdrive 2 and AMD EXPO technologies. With the launch of Zen 5, AMD also introduced an improved version of the Precision Boost Overdrive Overclockers toolkit. This toolkit allows us to manually adjust some of the parameters governing the Precision Boost boosting algorithm. The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC, and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly announced Curve Shaper for Zen 5. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we're simply enabling Precision Boost Overdrive. In the next strategies, we'll also explore tuning some of the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC limit will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking for AMD platforms supporting DDR5 memory. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If your motherboard supports EXPO, you can enable higher performance with a single BIOS setting. So it saves you from a lot of manual configuration. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tweaker to EXPO 2. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Despite the Ryzen 7 9700X having only 8 cores, the performance is restricted by its maximum power to 65 watt. By enabling PBO, we can easily double the power budget in all-core workloads. Combine that with enabling higher memory speeds, and it translates into significant performance gains across the board. The geomean performance improvement is plus 4.04%, and we get a maximum improvement of plus 18.07% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5061 MHz with 1.161 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 169.4 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5238 MHz with 1.257 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 173.4 watts. The boost frequency at one active thread is about 5549 MHz, and the average boost frequency gradually trails off to 5179 MHz when all cores are active. All cores can boost to over 5.55 GHz in single-threaded workloads. In our second overclocking strategy, we start our tuning work with the tools available in the Precision Boost Overdrive 2 toolkit. More specifically, we'll try to use Fmax Boost Override and Scalar. Fused Maximum Frequency, or Fmax, is one of the limiters governing the Precision Boost algorithm. It basically defines what is the maximum allowed frequency of any of the cores inside your CPU. Boost Clock Override, or Fmax Override, is one of the tools available in the PBO2 Overclockers toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. It's important to note that the Fmax override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. The programmed Fmax of the Ryzen 7 9700X is 5550 MHz. So with a plus 200 Fmax boost override, the new maximum boost frequency is 5750 MHz. Scalar is a tool that allows you to override the warranted stress level, or FIT, of your CPU. Essentially, you can increase it to 10 times the factory fused value. The tool's relevance shifts from architecture to architecture. For Zen 5 Granite Ridge processors, it appears Scalar is making a comeback in the overclocking strategies because the chips are very voltage limited. While the tool offers precise granularity, typically you'll find the available options to range between 1x and 10x in steps of 1 multiple. The effect of increasing Scalar is that the Precision Boost algorithm more aggressively pursues higher voltages as it is less concerned with CPU lifespan. The programmed VID limit is 1.4 volt, though we see slight excursions above that in really light single-threaded workloads. When all 8 cores are active, the maximum voltage is 1.35 volt. The programmed FIT value of this particular Ryzen 7 9700X is 1991.1. So, with a 10x Scalar, the new FIT value is 19,911. We find that in an all-core workload, the maximum voltage increased from 1.34 volt to 1.375 volt. That's not a big increase, but in voltage-constrained scenarios, every little bit helps. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tweaker to EXPO 2. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar Control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU boost clock override to enabled positive. Set max CPU boost clock override to 200. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Adding a little bit of extra frequency and voltage headroom doesn't appear to have too big of an impact in most benchmarks, as only single-threaded workloads show signs of improvement. The geomean performance improvement is plus 5.07%, and we get a maximum improvement of plus 18.22% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5052 MHz with 1.155 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 168.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5236 MHz with 1.249 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 172.8 watts. The boost frequency at one active thread is about 5566 MHz, and the average boost frequency gradually trails off to 5225 MHz when all cores are active. 2 out of the 8 cores can boost to over 5.7 GHz in single-threaded workloads. In our third overclocking strategy, we finally start the undervolting using Curve Optimizer. Curve Optimizer is one of the most well-known tools of the Precision Boost Overdrive 2 toolkit. It is most commonly known for its undervolting capabilities, but on AMD Ryzen CPUs, it also kind of acts as an overclocking tool. Let me explain how that works, and let's start with the voltage frequency curve. Simply put, a voltage frequency curve describes the relationship between an operating frequency and the voltage required to operate at that frequency. Here's the default voltage frequency curve of my Ryzen 7 9700X processor. We can immediately make a simple and redundant observation. The higher the frequency, the more voltage is required. For example, we only need 1.1 volt for a frequency of about 4.9 GHz. However, we need over 1.3 volt for a frequency of more than 5.5 GHz. We also notice that the maximum allowed voltage is 1.35 volt when all cores are active. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum possible frequency at 1.35 volt. With the default curve, that's about 5520 MHz. However, the programmed maximum frequency for the Ryzen 7 9700X is actually 5550 MHz, so we missed out on about 25 MHz. And as I showed in the previous overclocking strategy, we can use the Fmax boost override tool to increase the Fmax by another 200 MHz. So we're really missing out on about 225 MHz. If we set a curve optimizer to -30, we can shift the entire voltage frequency curve along the voltage axis. And suddenly, we need a lot less voltage for every operating frequency. For example, for 5 GHz we needed about 1.126 volt by default, but with a -30 curve optimizer, now we only need 1.03 volt. Moreover, the frequency is also boosting higher. The highest frequency with all 8 cores has increased by 180 MHz to almost 5700 MHz. These higher frequencies are now possible because our curve optimizer undervolting pulled them below the 1.35 volt threshold. Curve Optimizer is a very powerful tool. It's simple but not simplistic. And the more you dig into the details of how it works, the more intricate it becomes to figuring out how to apply it to your daily overclock. The traditional approach to overclocking AMD Ryzen CPUs is to undervolt the CPU by applying a negative curve optimizer. That helps in 2 ways. First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies. So you tend to get lower temperatures and higher performance. It's a win-win, though there are a couple of caveats when it comes to using Curve Optimizer. Curve Optimizer impacts the entire voltage frequency curve. So it affects the stability across the entire range of operating frequencies from 600 to 6000 MHz. The same curve optimizer value also impacts differently across the curve. If you're lucky, your CPU undervolt margin matches exactly how curve optimizer works. And in that case, you'll be able to really maximize the performance out of your CPU. But if you're unlucky and some parts of the VF curve have not enough undervolting margin, well, then your curve optimizer journey is going to be a rough ride. Curve optimizer is available on a per CPU, per CCD, and per core basis. The manual tuning process with Curve Optimizer can become quite convoluted because it spans the entire range of workloads, from light single-threaded workloads all the way up to heavy all-core workloads. In the past, I typically spend a lot of time on per-core curve optimization. With this particular CPU, however, I could simply set an all-core curve optimizer of -35 and it maxed out every core's single-threaded Fmax. So there wasn't much fine-tuning to be done. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tweaker to EXPO 2. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar Control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer step menu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 35. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Undervolting with Curve Optimizer is a Ryzen overclocker's best friend and has been for a very long time. It provides this Ryzen 7 9700X with a nice frequency and performance bump. The geomean performance improvement is plus 7.91%, and we get a maximum improvement of plus 21.77% in AI benchmark. When running the OLCCT CPU AVX2 stability test, the average CPU core effective clock is 5344 MHz with 1.143 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 163.8 watts. When running the OLCCT CPU SSE stability test, the average CPU core effective clock is 5508 MHz with 1.229 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 164 watts. The boost frequency at one active thread is about 5735 MHz, and the average boost frequency gradually trails off to 5506 MHz when all cores are active. All 8 cores can boost to nearly 5.8 GHz in single-threaded workloads. In our fourth overclocking strategy, we focus on improving the performance of the memory subsystem. Now, on AMD Ryzen CPUs, there are 3 parts that will affect the performance of the memory subsystem: the Infinity Fabric, the memory controller, and the system memory. They're more commonly referred to as the F-clock, the U-clock, and the M-clock. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 9 9700X, we can tune them independently. There were 3 things I wanted to address with the memory subsystem performance optimization. I want to increase the F-clock as high as possible, I want to run the U-clock and M-clock in sync, and I want to tighten up the memory timings. The fabric frequency, or F-clock, is generated by the SoC PLL, derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. While it can run independently from any other clock domain, it is still suggested that running the fabric clock in sync with the system memory and memory controller frequency provides the optimal performance point. That said, it doesn't seem there's much overclocking headroom beyond 2100 MHz. I managed to set 2200 MHz for this overclocking strategy. However, any steps above that couldn't boot reliably, not even with voltage adjustments. Speaking of voltage, The Infinity Fabric voltage is provided by the VDD-G voltage supply derived via an integrated voltage regulator from the VDD-CR miscellaneous voltage rail. There's a total of 2 VDD-G voltage rails available for manual adjustment. Note that the VDD-G voltage does not automatically adjust with VDD-CR miscellaneous. So if you need to increase VDD-G, for example to support higher memory frequency, you will need to change it manually. AMD Granite Ridge has 2 DDR5 Unified Memory Controllers, or UMC in short, and each provides 2 32-bit memory channels. The memory controllers are located in the I/O die and are therefore identical to the memory controllers on the Ryzen 7000 Raphael processors. Note that the Ryzen 8000 Hawkpoint processors actually have a newer memory controller. The Unified Memory Controller frequency, or U-clock, is derived from the UMC clock, one of the SoC PLLs. The UMC clock is driven by a 100 MHz reference clock derived from either an internal or external clock generator. The memory controller frequency is tied directly to the system memory frequency. It can run at either the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when enabling EXPO, often the motherboard auto rules will drop the memory controller frequency to half that of the memory frequency. We can easily force the memory controller to run at the same frequency as the system memory by setting uclock div1 mode to uclock equals memclock. I also suggest enabling SoC Uncore OC mode to disable all power-saving technologies affecting the clock frequencies of the memory subsystem. The VDD-CR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for various IP blocks, including the memory controller. The VDD-IO MEM voltage rail is related as it provides the external power for the VDD-P DDR5 bus signaling. The last piece of optimizing our memory subsystem is, of course, memory timings. To tune the memory timings, I rely in part on ASUS memory presets and in part on the experience from previous SkatterBencher guides. ASUS memory presets is an ASUS overclocking technology that provides a selection of memory tuning presets for specific memory ICs. The presets will adjust the memory timings and voltages. The ROG Crosshair X670E Hero motherboard sports 14 memory profiles for a variety of memory ICs and configurations. Since we're interested in simply adjusting the memory timings, we can try the Hynix 6400 MHz 1.4 volt 2x16GB single rank preset. Note that I stick with the EXPO primary timings and only leverage the memory preset for the secondary and tertiary subtimings. Regular viewers of this channel will know that I've tried this very particular profile in previous SkatterBencher guides using Hawkpoint. For the Hawkpoint APUs, I had to adjust the TRS timing a little bit to get rid of some annoying green flashes, but other than that, the memory was stable. However, for this system, the memory is stable for the benchmarks, but it doesn't pass the OCCT memory stability test. So I wouldn't consider this a stable system. That said, it serves a useful purpose for this guide to illustrate the performance improvements from tuning memory timings. I'll figure out the root cause of the instability in later guides. After tuning our memory subsystem, the AIDA64 performance improves quite significantly. We got about plus 20% extra performance by enabling EXPO and another 16% on top of that by tuning the memory timings. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tweaker to EXPO 2. Enter the DRAM Timing Control submenu. Enter the Memory Presets submenu. Select Load Hynix 6400 MHz 1.4 volt 2x16GB single rank and click OK. Leave the Memory Presets submenu. Set TCL, TRCCD and TRAS according to the EXPO kit. Set TRAS to 38. Leave the DRAM Timing Control submenu. Switch to Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set Infinity Fabric Frequency and Dividers to 2200 MHz. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency in dividers submenu. Leave the DDR and Infinity Fabric frequency timing submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar Control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 35. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC on Core OC mode submenu. Set SoC on Core OC mode to Enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Tuning the memory subsystem has a surprisingly large impact on the benchmark performance. The standout performance improvement is PY Prime, where we see a maximum improvement of plus 40.25% over stock, but that's very much a memory benchmark. We also see a performance uplift of 5 to 10 percentage points in other multi-threaded benchmarks, such as Geekbench and AI Benchmark. The geomean performance improvement is plus 10.67%. In our fifth and final overclocking strategy, we make use of eClock. eClock stands for external clock and is exactly what the term suggests. We can use external clock generators. And using the external clock generators, we can warp the precision boost algorithm to use higher frequencies. The standard Granite Ridge platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. In addition to the standard internal CGPLL, Granite Ridge supports up to two external clock modes. They're called eClock 0 mode and eClock 1 mode. In eClock 0 mode, an external 100 MHz reference clock is used for both the CPU and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks and the PCIe and SATA clocks. In eClock 1 mode, there are two distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. The overclocking strategy with eClock is the polar opposite of what we're used to with Ryzen CPUs. OC strategy number 3 illustrates that Ryzen overclocking is typically done with a negative curve optimizer. That pushes the precision boost algorithm to reach higher boost frequencies. With eClock, we still rely on the same factory fused VFD curve like we do with Curve Optimizer. It's just that we use the reference clock to stretch the precision boost frequency. Now, a tricky part of using eClock is that we apply a linear stretch on a non-linear VF curve. Here you can see two VF curves of the Ryzen 7 9700X. The default curve and the one from overclocking strategy number 3 with the minus 35 curve optimizer. We can see the law of diminishing marginal returns in action. The higher the frequency, the less additional frequency with every step of additional voltage. For example, on the default curve, increasing the voltage from 1.1 volt to 1.2 volt gives an extra 350 MHz, but increasing from 1.2 volt to 1.3 volt only gives an extra 150 MHz. The law of diminishing returns also applies to our Undervolt. With a minus 35 curve optimizer, we get an extra 400 MHz at 1.1 volt, but only 150 MHz at 1.3 volt. If we increase the eClock by 4.3%, setting it to 104.3 MHz, then the resulting curve looks as follows. We can see that the frequency increases by about 200 MHz across the entire curve and doesn't show any diminishing returns. The consequence in the real world is that we lack frequency improvement at the lower end of the curve and may have too much at the upper end of the curve. Before Ryzen 9000, we could squeeze more performance using eCLK and then also adopting a positive curve optimizer. A positive curve optimizer would sacrifice frequency at the lower end of the curve, so we'd have lower performance, but it would ensure stability at the upper end of the curve. So some sacrifice had to be made. With Ryzen 9000, that's different because now we have Curve Shaper. Curve Shaper is the newly announced tool of the Precision Boost Overdrive 2 toolkit. It was introduced alongside the Zen 5 Ryzen 9000 Granite Ridge processor. I had an in-depth look at the tool in a different video on this channel. In theory, it seems Curve Shaper is pretty straightforward. You get 15 additional tunable points across the VF curve. But the devil is in the details because AMD's Precision Boost 2 technology doesn't really work with VF points. So instead of getting a list of specific tunable VF points, we get 5 regions and 3 temperatures. The regions have a bit of a vague terminology and are not clearly defined. I will get back to that in a minute. The temperature points are more straightforward as they're defined as -5, 50 and 90 degrees Celsius. The idea of Curve Shaper is that you can adjust the voltage frequency curve in more specific areas than with Curve Optimizer. In our case, however, we want to claw back the undervolting potential at the lower end of the voltage frequency curve. For this purpose, we can set the low and medium frequency shaper points and apply a negative shaper magnitude. When we set the values to -30, this is what happens. Thanks to the different curve shaper points, we've successfully returned to our aggressive undervolt in the lower regions of the VF curve. However, we maintain the voltage at the upper end of the curve to ensure stability at the highest frequencies. This is a perfect illustration of the strength of Curve Shaper. The manual tuning process using eCLK can become quite convoluted because it spans the entire range of workloads, from light single-threaded workloads all the way to heavy all-core workloads. My eCLK tuning process for this Ryzen 7 9700X was as follows. First, I tried to find the maximum stable frequency in all-core workloads. Second, I tried to undervolt the lower end of the VF curve as much as possible. And then third, I tried to increase the maximum frequency in the 1T workloads. As usual, the requirement for stability is that we pass all of our benchmarks and the OCCT stability tests. For my system, I could run the OCCT memory test with all cores at 105.5 MHz, yielding 5.8 GHz. However, the system crashed when trying the stability tests, so I had to settle for 104.3 MHz. The undervolting with Curve Shaper went exceptionally well, and I could set both the low and medium frequency shaper magnitude to -30. Then, lastly, I could increase the Fmax boost override to +200. That should give us a theoretical Fmax of 5997.25 MHz. However, keep in mind that there is a 1.4 volt precision boost voltage limit at idle and 1.375 volt under load. So the maximum idle frequency we actually get is about 5860 MHz. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tweaker to EXPO 2. Set eCLK mode to asynchronous mode. Set BCLK2 frequency to 104.30. Enter the DRAM timing control submenu. Enter the memory presets submenu. Select Load Hynix 6400 MHz 1.4 volt 2x16 GB single rank and click OK. Leave the memory presets submenu. Set TCL, TR, CCD and TRAS according to the EXPO kit. Set TRAS to 38. Leave the DRAM timing control submenu. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set Infinity Fabric Frequency and Dividers to 2200 MHz. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency Timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Shaper submenu. For low and medium frequency, set low, medium and high temperature to enable. For low and medium frequency, set sign to negative. For low and medium frequency, set magnitude to 30. Leave the Curve Shaper submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Overclocking with asynchronous eCLK is somewhat of an academic exercise because its main purpose is to overcome the Precision Boost Fmax limit in 1T scenarios. We can see there is a small performance improvement in single-threaded benchmark applications, but for the most part, the performance is similar to what we get when we just use Curve Optimizer. The geomean performance improvement is plus 11.51%, and we get a maximum improvement of plus 40.13% in PY prime. When running the OLCCT CPU AVX2 stability test, the average CPU core effective clock is 5391 MHz with 1.15 volts. The average CPU temperature is 95.5 degrees Celsius. The average CPU package power is 172.5 watts. When running the OLCCT CPU SSE stability test, the average CPU core effective clock is 5494 MHz with 1.222 volts. The average CPU temperature is 95.2 degrees Celsius. The average CPU package power is 172.1 watts. The boost frequency at one active thread is about 5758 MHz, and the average boost frequency gradually trails off to 5454 MHz when all cores are active. All 8 cores can boost to well beyond 5.8 GHz in single-threaded workloads. Alright, let's wrap this up. This was my very first attempt at overclocking a Zen 5 Ryzen 9000 CPU. And I must admit, the overclocking experience was pretty cool. First of all, the overclocking headroom on this Ryzen 7 9700X was pretty good. I even had to use eCLK to squeeze out all of the possible megahertz. In addition to that, there's actually quite a lot of headroom for people that just enable Precision Boost Overdrive. The 65 watt default power limit is pretty low, and just by enabling Precision Boost Overdrive, we can easily double or even triple the power available. In addition to that, it was kind of interesting to see how much impact tuning the memory timings had on the performance. I would have never expect to see a performance improvement of almost 30% in AI benchmark. Lastly, Curve Shaper is a very useful tool in the Precision Boost Overdrive 2 toolkit. I think it's going to be really useful for Ryzen 9000 overclocking experiences. Basically, Curve Shaper made the asynchronous eCLK strategy viable. Anyway, that's it for this video. I thank you for watching, and I thank the patrons for the support. Obviously, I'll do more Ryzen 9000 overclocking guides in the future with the 16, 12, and 6 core as well. For those who want to read through my guides, read through the settings, and have a look at the benchmark results, I'll also put a written version of this video up on my blog. And that's it. See you next time.